I want to start us off with this example chemical reaction that I have on the board. I mentioned to you guys the ozone cycle when we were talking about bond formation and bond breaking. And this is kind of a version of the ozone cycle. So I want you to look at this where you have diatomic oxygen, O2, atomic oxygen, O, diatomic oxygen again, and then coming back to elemental oxygen, O3, before there's some decomposition again back to O2. So I want you guys to look at this reaction and decide where you think is energy required and where do you think energy is given off. Thinking about how energy is required and how energy is given off during bond formation and bond breaking. What parts of the ozone cycle do you think absorb energy and which parts release energy? Talk with the people around you, see if you guys agree, or see if you can identify what's holding you back from determining where energy is absorbed and where energy is lost. Can you use that graph to support what you're saying? Or is there not enough information to use that graph? Mm. Why? You're saying something's missing. I haven't filled that in yet. That's true. Well, tell me, does it take energy to break a bond? Or is energy given off when a bond is broken? How does this graph demonstrate it? Jordan? Energy is required. Here they're bonded, and they're in this energy well. Here they're not bonded, and they're at this higher energy. So if I want to break a bond, I have to put energy into the system. So Ryan, is there a bond here? There must be. We're going to talk more about that today. But if those atoms make up a molecule, then they must be bonded to each other. Is there a bond here? No. So a bond has been broken. And we don't actually know yet, but it's actually two bonds that have been broken. That's okay. Then what happens from atomic oxygen to ozone? A new molecule of O2 comes in. Is a bond created or destroyed in this step? Created. So what is energy doing here? Being produced or being taken in? Produced. A bond is formed. So these atoms are coming close together, dropping in energy, giving off energy. What I haven't shown here is that this is where UV light comes into play. This is the ultraviolet light that splits apart your diatomic oxygen and creates these radical oxygen species that can then react with more diatomic oxygen, the oxygen we breathe, to make ozone, which is not the oxygen you breathe. And then what happens in this final step, where O3 cleaves into O2 and O? Is energy absorbed? Is energy taken in? Or is energy released? Is energy given off? Can you identify whether a bond is made or broken in that step? Carly, what do you think? Bond is broken. I go from having 3 atoms in a molecule to having 2 different molecules. Energy required or energy given off? Required. So this is actually another step where more ultraviolet light can come into play. This is typically a lower energy ultraviolet light, and that's why our ozone is good at absorbing UVC A and UVC B, those higher energy wavelengths of UV. Okay, good review on bonding. We're going to talk more about the nature of those bonds. So on your handout, anybody not get the handout? On your handout, you've got this top section, polarity in bonds. I know there are two sides, so flip to the page that has polarity in bonds. First of all, I want to check that you guys already have a definition for polarity. Maybe you don't actually have a well-formed idea of polarity, but there's some common use of that term, and I want to capitalize on what you guys already understand about it. What does that word evoke in you? What do you think of when you hear polarity? Not just in a chemistry class, but in general. The Earth's poles, the magnetic poles of the Earth and in general. Anything else about polarity? Opposite charges. Great. So like a proton and an electron. You've got this polarity between them. Opposites attract. And there's also a lot of polarity in the political climate, right? This is a term that's often put in there because you get these two ends of a spectrum. And so we talk about that polarity. In chemistry, when we talk about polarity, we're talking about opposite charges. We're talking about things that are not even. And yet, most of the time, things that are polar can be neutral. So it's not so much that I have an imbalance between protons and electrons, but I have an imbalance of where I find those charges across two atoms that are bonding or across an entire molecule. So we're just going to look at polarity and bonding. This is when electrons are not equally shared. And we said that a covalent bond, one that allows valence electrons to be used for both atoms, they share those electrons. Okay, well, we're saying that they're just not equally shared. One of them actually gets to control the electrons more. The electrons spend more time around one of the atoms than the other. Of course, there are bonds that are not polar. We call these pure bonds. I don't know that I like the term pure bond. Kind of makes it seem like other bonds can't be pure. But this is one atom bonding with itself. So for instance, the hydrogen-hydrogen bond, HH, not to be confused with a hydrogen bond, which is very different. We'll come back to it. This is an atom bonding with itself. They have the exact same pull on the electrons. So we say that this bond is pure. I want you guys to look at your sheet. Can you find all of the other pure bonds that are on your sheet and label them above or below as pure? How many did you find? 3? The carbon-carbon bond, nitrogen-nitrogen bond, oxygen-oxygen bond. Now, what we haven't really addressed is that this line is our bond, and that it actually represents 2 electrons. That's an assumption that we have to agree upon. If you don't want to agree to it, sorry. I don't make the rules, but I do enforce them. So we're talking about 2 electrons here with this line. So let me ask you about this bond. If this one line is 2 electrons, 2 lines is 4 electrons. How would we differentiate those types of bonds? Good. We can call this a single bond, and we can call this a double bond. Do you think that this is a pure bond? The carbon-carbon double bond. On your sheet, you have the carbon-carbon single bond. Does it change when it's a carbon-carbon double bond? No, it's the same element. They're just sharing more electrons, but again, they have the same pull on the electrons. What happens now when I have diatomic nitrogen? This, by the way, makes up 78% of our atmosphere. This is what is in your lungs to the greatest amount. What would we call this bond, Ryan? Triple bond. And this is sharing how many electrons? And do you think that this is a pure bond? Or do you think that there is polarity, that one atom has the electrons more than the other? No. This is still a pure bond. Okay. If it's not a pure bond, then it can be a nonpolar covalent bond. To be fair, all pure bonds are nonpolar covalent bonds, but not all nonpolar covalent bonds are pure bonds. We say that this is a bond where the difference in electronegativity between the 2 atoms is less than or equal to 0.4. We're going to have to define electronegativity in order to understand what that means. And then there's another class of bond, which is the polar covalent bond. And this is where the difference in electronegativity is greater than, I think I got that wrong. It's greater than 0.4, but it's less than or equal to 1.9. So the difference, in electronegativity is this range. From this point to this point, we call it a polar covalent bond. And if the difference in electronegativity is greater than 1.9, we have one other bond type. And we already addressed it. Do you remember the first bond type we looked at in this module? The ionic bond. If the discrepancy between these atoms is so large, they don't share electrons at all. And we say that it becomes ionic. Electronegativity, which we'll abbreviate as En, is this tendency for an atom to pull on electrons. It's not the same as effective nuclear charge, because we said that effective nuclear charge is the same for all atoms in a family, but not all atoms in a family have the same electronegativity. This is the tendency of an atom to pull on electrons. How well does that atom pull electrons towards itself? If you have your periodic table, and if you don't, I have another one for you. If you have your periodic table, I want you to look at it and recognize that electronegativity increases as you go up a row, and it increases as you go across. Does anybody need their periodic table? So based on that, consider the atoms carbon, nitrogen, and oxygen. Which of those atoms is the most electronegative? Carbon, nitrogen, oxygen, all in the same row. Which is the most electronegative? Did I hear nitrogen? Most electronegative. Oxygen. Because we have carbon, nitrogen, oxygen. As we move to the right, electronegativity increases. What about the family fluorine, chlorine, bromine, and iodine? Fluorine. In fact, electronegativity doesn't really apply to our noble gases because we use electronegativity to describe bonding patterns, and the noble gases don't bond often. So our most electronegative atom is fluorine, and we give it this value, electronegativity 4.0. That number has no unit, and it doesn't really have an intrinsic value. It's just a number we're going to work with. Deal? On your periodic table, what do you think the least electronegative atom would be if you were just following this trend of up and over? Good. Pick the bottom left, francium. All right, now for this, the rest of this polarity in bonds assignment, you're going to need to have electronegativity values in front of you. So I'm going to pull those up. And what I want you guys, you can also pull them up on your own. I don't know that this image on the screen will be the biggest. And what I want you guys to do is calculate the differences in electronegativities for all of the bonds that you see here and label them as nonpolar covalent or polar covalent. You've already labeled the ones that are pure. I want you to label the rest of them as polar covalent or nonpolar covalent. And I have an image actually that I want to show you, but I lost it, which is always the best place for it to be. All right, sorry, here we go. A student of mine actually made this after listening to me talk once about electronegativities. Since electronegativity is this pull on electrons, I like to think of that as falling into kind of a gravitational well. And there are some periodic tables you can find that have electronegativity values. And some of them are 3D, so they show you the difference in electronegativity values by height, but they often put fluorine, being the most electronegative atom, as the tallest. But this is a bit misleading because fluorine, being the most electronegative, pulls on electrons the most, and having it at the tallest makes it seem like it's the least stable, like electrons would flow away from that. So a student made this once where he put fluorine as the lowest, because imagine, put electrons anywhere, and where are they going to flow but towards that lower atom? What's weird about this periodic table? Right, it's flipped from what you're used to looking at. Your periodic table puts fluorine on the top right, but if fluorine was the lowest, you'd never see it up there. So he just flipped it around for you. So you can Google these values, or you can use what's on here. I want you to go through and calculate the difference in electronegativities for the remaining bonds on this page, and then label them. Are they nonpolar covalent, or are they polar covalent? you are given electronegativity values when you go to the midterm. False. They're not on your periodic table, which is why I have this up. And they're not on your useful equations sheet. For the most part, you will get familiar with these trends in recognizing bonds that are polar and nonpolar, which means you don't really need electronegativity values most of the time. However, if I were to jot down any on your cheat sheet, they would be those first two rows of main groups and your halogen families. Those are the most common. What I would encourage you to do is when you get to the practice test for unit 3 to 5, pay attention to what questions are being asked about polarity. Do you really need electronegativity values? Because that can be just empty space that shows up, or I'm sorry, wasted space that shows up on your sheet that you don't necessarily need. Get to know the trend, and that's about as useful as it can be. All right, why don't you guys turn towards each other and see how many did you get in that time? How many did you not get to? Are you surprised by any of these, being polar, non-polar? Yeah. Correct. Well, not to mention the pure. Right. All right, what did you find? How many of these bonds are non-polar? Anybody? Really, Ashley? Just one? Did anybody get more than one bond that was non-polar? What'd you get?
Oh, no, I got 2 calculations done.
Oh, you got 2 calculations done. Really? You're just doing subtractions?
Yeah.
Wait. Okay, let's see. There are some easier ways to go through this than others. So for instance, if you're going to do the top row, you're comparing hydrogen against all of those atoms. So get to know hydrogen's electronegativity, and then just subtract them. But actually, you don't even have to work that hard, do you? 2.1 and 2.5 is your first bond, C to H. The difference between 2.1 and 2.5, 0.4. We said that qualifies as a nonpolar covalent bond. Is there an equal tug of war on those electrons? No. Who made that determination? I don't know. Some guy. We decided that this is the line in the sand of which we will call this nonpolar and this polar. So I really hate to tell you this, but there is polarity in that bond. The electrons are not perfectly even, which is why it's not pure. But its behavior is less like that of the others, so we just call it nonpolar. I think it's terrible because we're trying to fit nature into our little boxes, and nature doesn't like to fit in our little boxes. If C to H is 0.4, which is literally the upper limit of what we call nonpolar, probably intentionally, then as I go towards more electronegative atoms, what is going to happen to my bond type? It's just going to be polar. Do I have to do any calculation? If carbon to hydrogen is just barely nonpolar, then nitrogen to hydrogen is definitely polar. Oxygen to hydrogen is definitely polar. And you'll find that nitrogen and chlorine have the same electronegativity. So that's also polar. Okay, so we only had to do one calculation, and we filled out the entire row. And now you know, when hydrogen's bonded to carbon, that's pretty much the only time it's in a non-polar bond. Hydrogen, other than being bonded to itself, hydrogen is often polar in its bonds. The second row, bonded to carbon. Well, of course, we know carbon to carbon was pure. What's the difference between carbon and nitrogen? 0.5. How different is that from 0.4? Not very. And yet we classify it now as a different bond type. We say that is a polar bond. Oh, but this is non-polar. Okay. Be skeptical of what you're told to call things, right? That's polar. Then what's going to happen to C to O? Also polar. And C to Cl? Also polar. So again, just one calculation, we got them all done. Now look at the third row. You've got the C to N double bond. We know the C to N single bond was polar. How does it change when there's a double bond? Does the math change? No. It's still the same electronegativity values. It's still the same math. So the C to N double bond is polar. Let me draw out some of this math for you guys, by the way. Difference in electronegativity. Let's pick the next one. Let's show O to N, where oxygen is 3.5, carbon is 3.0. I get a difference in electronegativity value, 0.5. N to O, polar. All right, I have a question. What if I didn't know which way to put those numbers in, and I plugged it in as 3 minus 3.5, and my difference in electronegativity is negative 0.5? Just ignore it. You're looking at an absolute value, an absolute difference, not whether it's more electronegative this way or more electronegative that way. Does that feel okay? Last row, C to O double bond. Polar or non-polar? We know the C to O bond was polar. The C to O double bond is polar. N to O double bond. Polar. And of course, we said the O to O single bond. Non-polar. So this is what we call polarity in bonding. We base it on differences in electronegativity. And we have these lines in the sand that said if it's this value or less, we call it non-polar covalent. Can you guys give me a bond that you know would be ionic? And then let's prove that an electronegativity difference greater than 1.9 is an ionic bond. Give me the bond of an ionic compound you know. One more time. Sodium chloride. Good, because it's an ion, so we change the suffix to IDE. Sodium chloride should be experiencing an electronegativity difference greater than or equal to 1.9, correct? I've got chlorine at 3.0. I've got sodium at 0.9. That's a difference of 2.1. What is this trying to tell you? What is electronegativity trying to say? It says put these electrons between two atoms. Where will you find them the most? Are those electrons sitting evenly between the two atoms, or are those electrons spending more of their time by one of the atoms and less by the other atom? To such a point where the electrons are actually never felt by one of the atoms, they're only felt by the other, correct? Ionic bonding, is it covalent? Does it share the valence electrons? No. So at a certain point in this electronegativity difference, you get so large, there is no sharing. It's just taking. Ashley. Good question. Do the electrons go to Na? Well, first of all, let's look at our periodic table rather than the upside down one, because this is the tool you'll want to use. How does electronegativity trend? Up and over, up and to the right. Let's look at where sodium is placed and where chlorine is placed. Are they different at all in terms of their row? Is one of them more up? No, they're in the same row, which means we can actually compare just by this difference in electronegativity. Chlorine is more to the right, which means that it should have a higher electronegativity. And electronegativity is what? It's how well the atom pulls on electrons. So who pulls harder, sodium or chlorine? Chlorine. So does that answer your question? Where would the electrons of the ion NaCl be? Would they be by sodium or would they be by chlorine? And that's why we have Na plus, because it doesn't have the ions, and it doesn't have the electrons, and Cl minus, which does have the ions. One last connection for you guys with electronegativity. Do you guys remember those terms we talked about last week? Ionization energy and electron affinity. What were they in regards to? These were some of our periodic trends. What is ionization energy? I see you guys flipping through your notes. That's what I want you to see. Energy required to pull an electron away from an atom. Who typically has the lowest ionization energy? Who is it that it is the easiest to pull electrons away from? Sorry? Oh, that's true, yes. The lower down you go, the easier it is. And actually, most of your metals, those are the easy ones to pull electrons from, correct? So these have low ionization energy. They also have low electronegativity. They don't pull on their electrons very hard. It's easy to pull their electrons away. And who has larger electron affinity? What was electron affinity? Energy given off when an atom accepts an electron. Who has larger electron affinity? Metals or nonmetals? The nonmetals have larger electron affinity because they'll give off more and more energy when electrons come to them. And who has larger electronegativity? Nonmetals. So we're seeing this trend. Electronegativity lines up with what we expect about ionization energy. Those atoms that pull on their electrons the least require the least amount of energy to get rid of them. And those atoms that pull on electrons the strongest give off a lot of energy when they get them. So it lines up with what we've already seen about how electrons behave around these species. Do you guys have questions on electronegativity? What's the opposite of electronegativity? Berkeley? Electron affinity is not the opposite of electronegativity. In fact, those are actually similar to each other. Electropositivity is the opposite. I don't think your textbook talks about this. I only just read it in a textbook last year for the first time. Never heard that term before. So if we say fluorine is the most electronegative, we can say that francium is the most electropositive, which is to say that it often gives up its electrons, whereas fluorine likes to take electrons. Okay, any questions then? That's it for Module 8. We're going to move on to Module 9 on Lewis structures. Lewis here, obviously a very descriptive term for a guy's last name. First of all, we're going to start off with Lewis symbols. Lewis symbols are actually pretty easy. We combine the elemental symbol, the chemical symbol, with valence electrons. Who remembers where to find valence electrons? They're common between families, true. There is a really easy way to figure it out. For main groups, this doesn't work as easily for transition metals, but for main group, S block, P block elements, it's just the name of their group. Group 5A, 5 valence electrons. Group 2A, 2 valence electrons. Who remember? Does anybody remember what valence means? I talked about it last week. It comes from the Greek for something. Comes from the Greek for powerful, because the core electrons are not doing any of the chemistry. It's the valence electrons that do chemistry. That's why Lewis structures only look at valence electrons. The core electrons are not doing anything. So I want you guys to fill out this table, but here's the rule about Lewis symbols. You'll take your element and treat it as if there's a box around it. We're going to have 4 sides. And that's because for our main group elements, we're often trying to follow 8 electrons in the valence shell. Treating it with a box around it, we're going to place valence electrons first individually and then in pairs. So for instance, if I had 8 valence electrons, I would start by just putting in 4 of them, 1 on each face, and then coming in to pair the electrons. Why do electrons pair? They're little magnets, so they like to be paired up with each other. But with Lewis symbols, just like with orbital diagrams, we're going to keep everything unpaired first before we start providing pairs. So, using your periodic table and this sheet, go in and fill out the Lewis symbols for all of these common elements we're going to be dealing with. You'll notice that this is pretty much just a selection of the non-metals. Since this looks like your periodic table, do you need to work hard going through the columns? Those are families. So when you figure out the number of valence electrons, you just copy it down to the next member of the family. you know why? Its valence shell is the first shell, and the first shell has how many subshells? The S subshell, yep, which can hold 2 electrons. You got it. We talked about that rule, correct? The octet rule. Atoms tend towards the octet rule. By the way, I didn't put group 1 or group 2 metals on your chart, so if you want to see what they look like, lithium, sodium, potassium, group 1, they all just have 1 dot. Beryllium, manganese, magnesium, calcium, group 2 metals, 2 dots. Okay, any of these that stood out as confusing, did you get them all? How many dots do you have around hydrogen? Just 1, because although it's not an alkali metal, it can still be shown as being a member of group 1A. For carbon, how many dots? So how many pairs do you have around carbon? No pairs. You should have no pairs surrounding the carbon, 1 dot on each side. What about for nitrogen? How many pairs? 1 pair. Does it matter whether that pair is on top, bottom, or the sides? No, it really doesn't. It does often show up on the top, but that's all you need to know. You know what? Instead of oxygen, why don't we talk about the sulfur that you guys saw? How many pairs around sulfur? Same as oxygen, 2 pairs. Does it matter if those 2 pairs are next to each other or across from each other? No, it doesn't matter, but it does have 2 pairs and 2 unpaired. And the halogens, how many pairs? 3 pairs. How many unpaired? Just 1. Once again, does it matter where the unpaired electron is? On which face? It does not. It's just that there's 1 unpaired electron. Great. This actually tells us something about most of these atoms. It tells us that in group 1A, this likes to make 1 bond. It's got 1 unpaired electron, likes to make 1 bond. Now the metals are different because they actually like to just give away their electrons. They have very low ionization energy, so they just give up their electron and make an ionic bond. But hydrogen likes to make 1 bond. The halogens like to make 1 bond, a single bond. That's what they prefer to make. What does hydrogen and the halogens have in family? Have in common? Excuse me. Good. Hydrogen gets 1 more electron. Its outermost shell, the first shell, is satisfied. Duet rule. The halogens get 1 more electron. Actually, for most of them, it doesn't actually fill their outermost shell, but it fills their S and P subshells and obeys the octet rule, and that's good. In addition to just these will fill their shells, what else do they have in common? The symbols. They have 1 unpaired electron. That unpaired electron tells you how many bonds it likes to make. How many bonds do you think sulfur and oxygen like to make? 2 bonds. Talk to me about water. H2O. How many bonds does oxygen have? 2. Look at every organic molecule that has oxygens in them. you'll see that unless it's a charged oxygen, it has 2 bonds. What about nitrogen and phosphorus? How many bonds do they prefer to make? 3 bonds, because they have 3 unpaired electrons. And carbon? Carbon likes to make 4 bonds. We call it tetravalent. Tetra meaning 4. Carbon really likes to make 4 bonds. The thing is, you're going to be showing molecules and how they're structured. And this is that cheat code. If you don't see oxygen with 2 bonds, maybe something's wrong, or there's a hint for you that there's going to be a charge in there somewhere. If nitrogen has 4 bonds, there's going to be a charge. If it has 3, it's relatively happy. So this is not a very common thing for us to see. We won't see Lewis symbols a lot because we're going to start combining them into molecules. But it is a hint about what these atoms like to do in molecules. The other way that we can show these Lewis symbols is in ion formation. For instance, sodium chloride. We can imagine a chemical reaction that begins with sodium elemental, not sodium ion, and atomic chlorine, not necessarily elemental chlorine, Cl2. Notice that there's 1 electron on sodium, 7 electrons on chlorine, and these will preferentially become Na plus and Cl minus, where now Cl minus has 4 pairs of electrons, an octet. Chloride has its 8 electrons. Sodium has an empty outer shell, which means it's about as stable because now its next highest energy shell is completely filled. Right? Now I want to talk about this, charges. In chemistry, we often talk about partial charges, which we're going to come back to later on in regards to polar bonds. But we also talk about formal charges. There's a lot of different ways to think about formal charge. Your textbook says that formal charge is a bookkeeping method. It just says, given how many protons and how many electrons you have, what type of charge is there in the system. But formal charge can also pinpoint an atom where there's a charge discrepancy. This atom has more electrons around it than maybe it should. Oxygen likes to make 2 bonds. What if it only has 1? What if it has 3 pairs of electrons like a halogen? That oxygen now experiences more electron character, more negative charge, and so we represent that with this formal charge. Formal charge can be calculated. We use this equation. Formal charge equals the number of valence electrons. I actually have this for you on your sheet, by the way, right underneath formal charge. Minus, all right, now on the sheet, I give it to you as the number of non-bonding electrons plus, oh, I'm sorry, you'll need to make that fix. I actually say non-bonding minus. I meant to put non-bonding plus. Non-bonding plus 1/2 of bonding electrons, not minus. You guys all got that fixed? Good. Oh, but that's so wordy. So here's what I want to say instead. The number of dots, because each dot is a non-bonding electron. That's an electron that stays with this atom, as opposed to the bonds that we saw earlier, the lines. Those were covalent electrons. Those are electrons that are bonding. And we're only counting one of those two electrons in a line, which is why the equation says plus 1/2 the number of bonding electrons. So you can just count the number of lines. If you have a double bond, 4 electrons, half of that is 2. If you have a double bond, you just have 2. So this part of the table is actually more empty. You guys will need to go through it with me to fill in some lines and some dots. So let's look at hydrogen with a dot, hydrogen with 2 dots, and hydrogen with no dots. We'll calculate those formal charges. Carbon with 4 lines, carbon with 2 double lines, and carbon with 3 lines. We'll go through and we'll calculate those charges. Nitrogen. We'll go from nitrogen with 3 lines, 2 dots, nitrogen with 2 lines, 2 pairs, and nitrogen with 4 lines. Something similar with oxygen. 3 pairs in 1 line, 2 pairs in 2 lines, 1 pair in 3 lines. And we'll look at a representative of our halogen family, fluorine. You'll notice we're not doing the bottom row yet. We're going to talk about those atoms in a little bit. Once you get these copied down, I would like you guys to work with each other for the next 5 minutes to fill out this table of formal charges. And to be fair, there are no patterns inherently in this table. I just want you to get familiar with what you're seeing. Once you've decided that an atom has a negative charge, draw it next to the atom as this negative. Once you've decided an atom has a positive charge, draw it next to it as this positive. Remember that you're looking at pairs and non-bonding electrons as these dots. And I want to apologize. Can I make one change quick? Can we take this hydrogen that's at the top and actually just show it as a line instead of 1 dot? Instead of just H dot, let's put H line. That's where I'd rather you practice. Work with your neighbors. Take 5 minutes. See how many of these you can get through. if you feel confident on what you're doing, you should find someone who doesn't feel confident and explain it to them. Walk them through how to do it, and then ask them to apply it. You'll learn even more when you try to teach someone else. If you want me to check some of yours to see that you're on the right track, raise your hand. Show like the negative sign, or show the positive sign.
Wait, so the big ones are already down, range down. Like we're using things. You got it. Yeah. Then dash line. I think it's like as you go up, but it normally helps.
The H line.
Oh.
I did have a dot.
So all of these just have one big line.
What does the dot mean?
So one
Means two electrons.
and then dots two plus zero.
So it's not just two electrons. These are different types, right? Non-bonding or the They're shared. What's the other atom? Doesn't matter. It's two electrons. We're going to take half of them. So which means I can really just count the number of bonds. Yep. Oh, that's okay. Yeah, that's good. All right. And it looks like you're on the right track. Good work. We're neutral. We're designing a neutral allowance. So, Joey, can you tell me how you did it? You're still getting
You get 8.
Yep. And we're going to take, actually, we're going to do
4 minus 0 plus 4. Yeah.
After this,
we're going to do equation. We're going to take all of the bonding electrons.
Like for nitrogen.
How many bonds?
Yeah. So I'm thinking the whole row.
What is which is why this one dot plus line. I just need one line. I count that one. That is the same thing. Correct. Good.
That's way right now. No, you're good. It's got, but it's okay, but it's not got. Dots are electrons that have, they're not shared. Probably not. Yeah, nitrogen.
On this case, correct.
5 minus 2 minus 2 plus 3. Those electrons is 5. Yep.
My
And
friend,
2 dot plus 3.
I hate this.
2 unshared electrons. So it's 5 minus. I'm distributing the way that I'm setting it up is I'm
Okay, you guys
distributing
feel confident? Yeah.
5 plus.
Yes, they are the same. I wanted to show you different ways those 4 lines can show up. You got it. Yep. The only thing that I would change is draw like a negative and a positive to show the charge. We represent charge with that plus sign and that minus sign more than we do with numbers.
Minus 3 is 5.
Also,
If you do 5 minus 2 minus 3,
yeah, you are. On the bottom, but you've got a line which we can do a bond, but that's a plus. Good.
I was thinking the whole row kind
You're right. Okay. Good work. Did any of you use this as a cheat sheet? Because I told you it is kind of a cheat sheet for recognizing bonding. Those neutral atoms, they all satisfy this. How many different ways do you have carbon with 4 bonds? 2. I've got 2 ways that carbon has 4 bonds. 4 single bonds, 2 double bonds. These should both be neutral on that carbon. What happens if carbon doesn't have 4 bonds? Well, there's 2 things that could happen. It could be carbon has 3 bonds, and that's it. Or it could be that carbon has 3 bonds and a lone pair, a non-bonding pair of electrons, but we don't see that. So to calculate the formal charge here, carbon has 4 valence electrons. There are no dots around this carbon, and there are 3 lines. 4 minus 3, positive 1. So I can show that with a positive charge next to the carbon. I had some good questions come up. If each line is equal to 2 dots, then should I say 2, 4, 6 dots and do 4 minus 6? No, because the line is bonding electrons. We're showing a bond when we show a line, not a pair that's being held for itself, a non-bonding pair. It's a good question. And the confusing thing is, what are these bonds going to? Anything you want. Other atoms of the same element. You could connect all of these like a big series molecule. Just imagine it's bonded to something else. That's what we're trying to get at, okay? All right, why don't you guys take a 5-minute break? Even if you're not going to leave, get up. Get your blood flowing before we come back in to look at Lewis structures. Yes, exactly. 1 minus 2, 1 minus 0.
I was just doing it like really quick, so I was like, am I doing it wrong?
No. That is a good way to do it. These are all 7.
Yeah.
So this valence number it's 7.
Okay, so you're right.
Correct.
Okay, cool.
Yeah. These are right. Correct. All of them are correct. Good job. It's the easiest math you'll do in chemistry.
Yeah.
Right?
That's why I was wondering if I was doing it wrong. It's crazy.
No, if it feels easy, you're probably doing it right. Anybody want me to check their work? Just let me know. Dahlia, you have school computer, right? Does yours time out, like screen dark after 5 minutes? I even had a student try to change fidget settings, so yeah. It's annoying because this happens to me a lot where I'm like halfway across the room and it times out. Yeah, not my favorite. Please do, yeah. Minchie's got a seat right in front of her. Absolutely. All right, guys. Two oddball types of elements that I want to talk about, and that's going to take us to the bottom row of this table we've got. Except I didn't put B on that bottom table, so you might want to add this one in. One of the more common things that we see in elements when they come into structures, into these molecules, is that many atoms don't obey the octet rule, but they can become hypervalent, just meaning a lot of valence electrons. And we can describe that as being an expanded octet, which is kind of funny. Like, we're not taking 8 and stretching it to just be a fatter 8. We're actually going from 8 to 10 or 12 or 14 electrons. Hypervalent or expanded octet species are in row 3 and lower. Because looking at your periodic table, thinking about the quantum chemistry we just learned about, first row only has one subshell, the S subshell, one orbital, 2 electrons. In the second row, we get 2 subshells. We introduce the p block, 3 p orbitals. In the third row, we introduce the third shell of electrons. That's 3s, 3p, and 3d. So if phosphorus or sulfur were truly going to fill their outer shell, they wouldn't need 8 electrons, they would need 18. They don't go for 18, but they can go above 8. This is because they have 3d orbitals. Notice that's not 3D like three-dimensional. Actually, you know what? We could abbreviate that better. We don't have to say they're 3D. They just have d orbitals. In the third row, it's 3D, but in the fourth row, 4D. In the fifth row, 5D. And then we have some electron deficient species, the most notable of which is boron. Which is, rather than trying to fill its outermost shell, the second shell, just like carbon, nitrogen, oxygen, and fluorine, boron actually prefers 6 electrons. Prefer is kind of an odd term. What I'm really saying is that boron is neutral and often takes on this bonding character. So I've got boron down here on the bottom left. If I give boron 3 bonds, let's look at its formal charge calculation. Formal charge equals 3 valence electrons minus 0 dots and 3 bonds. This is boron in a neutral bonding state. If I gave boron a 4th bond, if I gave it an octet, it would have a negative charge. That would be 3 minus 0 plus 4. So boron is neutral when it is electron deficient. But let's look at these phosphorus and sulfur species. Phosphorus is in the same family as what other element? Nitrogen. So we can see phosphorus with this neutral bonding state, just like we see nitrogen with this neutral bonding state. By the way, I didn't do this earlier. I probably should have. These are all of the charges that should have been on your sheet. So in case you didn't get them all, those are the ones we're looking for. Okay, but phosphorus can do this strange thing. Phosphorus can expand beyond 8 electrons so long as it's still neutral. And there are actually 2 ways that it can do this. It can take this pair of electrons that you see on top, and it can turn it into a double bond. 1, 2, 3, 4, 5 bonds. So fluorine has 7 valence electrons. We're looking at atoms in bonding situations here. So this is fluorine with 3 lone pairs and a bonding pair, 3 non-bonding pairs, 1 bonding pair. We can calculate it. Fluorine has 7 valence electrons, minus, there are 6 dots, and there's 1 line. 7 minus 6 plus 1. 0. This is a neutral fluorine. Remember, our symbols, our Lewis symbols told us halogens like to make 1 bond because they have this 1 unpaired electron. They want to get it paired. They'll do it by covalent bonding. Caden.
I think it just looks like there's only 1 dot at the bottom.
Is it that? Is that this is a pair?
Because that's what we did.
I see. Sorry about that. Yes. That makes a big difference if you don't count all of the electrons the same. Does that change your calculation?
Yeah.
All right, great. So here's our phosphorus, our first phosphorus with 5 bonds. How many electrons does that phosphorus atom have around it? 10. You'll notice this whole table obeys the octet rule, except for the first row, the first column with hydrogen. The rest of this table all obeys the octet rule. None of them have more than 8 electrons. This carbon cation actually has 6 electrons. It's not electron deficient because it's not neutral. It's positively charged. But phosphorus now expands beyond an octet. Phosphorus now has 10 electrons around it. We can also see phosphorus take on 5 bonds when they're all single bonds. The difference here is phosphorus with a double bond, phosphorus with 5 single bonds. I'm going to redraw a couple of my bonds to make this look a little bit more like a stick figure man with phosphorus as the chest. 5 bonds breaks the octet rule. Phosphorus is able to do that. Check for me again. What is the formal charge on phosphorus? In this bonding scenario, how many valence electrons does phosphorus bring? 5 valence electrons. How many dots around phosphorus? 0. And how many bonds? 5 minus 5? These are both neutral phosphorus species. They have no charge because they've expanded and they're in row 3 or lower. Let's look at sulfur. Sulfur is in the same family as what other major element? Oxygen. So we know that sulfur has 6 valence electrons. So we know that sulfur can bond in the same way that oxygen does, where sulfur can take on 2 bonds and 2 lone pairs. But sulfur can actually turn these pairs, these non-bonding electrons, into double bonds in a similar way to what we saw phosphorus do. How many electrons are surrounding sulfur now? 12 electrons. Is that an octet? No, that's hypervalent. That's taking on more than an octet. That's an expanded octet. What is the charge on that sulfur? 0. 6 valence electrons minus 6 bonds, neutral sulfur. Here are the other ways that sulfur can make this work. Sulfur can do 6 single bonds. It's in group 6. It can make 6 bonds. That's still 12 electrons around it. And sulfur can do this. Sulfur can take on 4 bonds plus keep a non-bonding pair of electrons for itself, a lone pair. Did I draw those as single bonds or double bonds? Double bonds. Do they have to be 4 double bonds in order to satisfy sulfur? It could have just as easily been 4 single bonds. But this is what we're saying, that if sulfur makes 4 bonds and keeps a lone pair, it will still be neutral. Can we prove it? 6 valence electrons. How many dots? How many bonds? 6. 6 minus 6, neutral sulfur. These are all neutral sulfur species. How fun is that? These atoms take on these characteristic bonding patterns in order to have a neutral charge. Okay, any questions? We're going to transition then from Lewis symbols into Lewis structures. And all of the things that we did with Lewis symbols, including formal charges, we can take to Lewis structures. Now we'll actually see what's at the other end of that bond. We're going on to the back side of this page, by the way. And you'll notice that I have some steps written out. They're not really numbered, they're just italicized. By the way, if you wanted to do this assignment again, or a friend didn't make it to class today and they want to do this, too bad. You're just going to have to do with this one copy. No, I'm just kidding. I'm going to upload this onto Canvas, and I'll put it in the Unit 4 module near the things that talk about Lewis structures so that you guys have access to this. Nay, I'll put this up towards the top of Unit 4 so that it's right next to the learning objectives sheet that you guys have. Okay, so Lewis structures aim to connect atoms in a molecule. We've been looking at chemical symbols. Now we want to expand that. So I want to take you guys through this example. It is CH2Cl2. It's an organic solvent that recently has been heavily EPA regulated due to its carcinogenic effects. And it was one of the most commonly used organic solvents in teaching labs and research labs for years. And then last year, the EPA said, this stuff will give you cancer. Maybe try not to use it. Pretty interesting. We want to show how the atoms are connected in this molecule. And we want to show where all of the electrons are. Which electrons are responsible for chemistry, for the nature of bonding and chemical reactions? Core electrons or valence electrons? So we only need valence electrons to show how this is connected. So step number 1, count all valence electrons. No more, no less. What happens if I have an ionic species? If I have a negative charge, that means that I need to add electrons. I have a surplus of electrons compared to what I would expect from these atoms. Anions add electrons. A -1 anion, 1 electron. A -2 anion, 2 electrons. Cations do what? Good. You'll have less electrons than you would expect. Do we have any charge on this compound? None. Great. How many valence electrons for carbon? Good. I've got 1 carbon atom, and that's 4 valence electrons. How many valence electrons for hydrogen? 1. Since I have 2 hydrogens multiplied by 1, all hydrogens are bringing a total of 2 valence electrons. How many valence electrons for chlorine? 7. Group 7. And I have 2 chlorine atoms. So I'm bringing a total of 14 electrons from them. My Lewis structure needs to include no more, no less, 20 valence electrons. That's step one. It is crucial. Once you get down how to build Lewis structures, you don't need to do this. You can often just figure it out. But if you feel like you're still learning Lewis structures, this is step one. All right, step number two, and I'm gonna put it here. We place the least electronegative atom in the center, except hydrogen. When we say in the center, we're saying that it's going to bond to the other atoms. But hydrogen can't bond to more than one atom. So despite often being the least electronegative, we never place hydrogen in the center. Which of my atoms then will go in the center? Carbon, hydrogen, or chlorine? Carbon. Now, similar to last time with Lewis symbols, we can treat this like a square, and we can just place our 4 atoms around carbon as a square. But I do want to remind you that we are going to go beyond squares at some point. We'll have to get to these 5-sided shapes and 6-sided shapes. So it's a bit arbitrary. You can kind of go where you'd like. Does it matter where I put the atoms? No. H, H, Cl, Cl, it's all the same. Now step number 3, I don't know if, maybe I just put a typo in there. I say single bond once, and I think I really meant to say single bond everything. Everything should be single bonded to something. All of the atoms need to be connected. These aren't ions that are just floating on their own, experiencing ionic forces. These are covalent atoms. They're sharing electrons, so there must be electrons between them. So I'll draw a single bond between H and C, a single bond between C and Cl. And now what I'm going to do is figure out how many valence electrons I've used. I had 20. I've used 2, 4, 6, 8. How many do I have remaining? 12. I still need 12 valence electrons in this Lewis structure. Listen, other people are going to tell you to build Lewis structures other ways. They're going to say, take the Lewis symbol, place the Lewis symbols next to each other, and align the unpaired electrons as a bonding pair. That's okay. It teaches you that these atoms come together out of nowhere, and that they all come with the correct number of valence electrons, and that their valence electrons come together to form these bonds. That might happen after a supernova, when a star is just emitting all of these atoms, and then they find their way together. But for most chemicals that you encounter in your life, they did not form by carbon coming with 4 valence electrons, and hydrogen coming with 1 valence electron, and chlorine coming with 1 valence electron, or excuse me, 7 valence electrons, but 1 that is unpaired. That's how some people would tell you to do it. Bring the Lewis symbols and just place them together. It's okay, but it's not like how the molecules form. So if you have the total number, you know everything has to have at least a single bond. This allows you to just jump straight to that without worrying about whose electrons are these, whose electrons are those. It's the molecule's electrons. They need to be in there. Is that okay? By the way, if you did do it this way, you can see that this orange and black pair becomes a bonding pair. This orange and black pair, this orange and black pair, this orange and black pair. That's all we're doing. We're just creating those single bonds. Okay, but I have 12 valence electrons left. So what's my next rule? Step number 4. Place the remaining electrons as lone pairs and we're going to place these on the outside atoms. Why? Because we already placed, I realize I have a pretty awful mistake here. I didn't say least electronegative, I just said place electronegative atom in the center. We already decided to put the atom that pulls on electrons the least in the middle. That would be the atom that is most willing to share. So why would it take remaining electrons? We're going to place remaining electrons on outside atoms first, then on the inside. And this is all with one goal. Fill octets. That's what we're aiming for. Blank, what atom does not need an octet? Hydrogen. So I'm not going to place any of my remaining electrons there. I'm only going to place these on chlorine, and then if I need to, I'll place them on carbon. All right, 12 electrons. I'm going to add them as lone pairs. Lone pairs, also called non-bonding pairs. And notice I'm not going to put these in one by one and then come back and pair them. I'm going to pair them immediately. 2, 4, 6, 8, 10, 12. Oh, that's it. That's all of my valence electrons. Did I satisfy everyone's octets? Hydrogen has its 2, chlorine 2, 4, 6, 8, 2, 4, 6, 8, 3 lone pairs, 1 bond, just the way we saw halogens like to bond. And carbon 2, 4, 6, 8, 4 bonds, just the way we saw carbon likes to bond. Dichloromethane, DCM. That's its structure. That shows how the electrons are involved in holding the atoms together. When I was in college learning how to do this, I would often use these circles to help me count my octets. So I'd look at an atom like this, and I would draw around all of the electrons that it touches. And then an atom like this, draw around all of the electrons it touches, and count those electrons. Because these are covalent electrons, you should be counting the same pairs of electrons for more than one atom. It's only 20 electrons, but they're satisfying more than one atom. Like carbon in the center gets a circle that's drawn around all of these bonds. These electrons count for both atoms. These electrons count for both atoms. And to clarify some of the terminology, this is the bonding pair, and this is a non-bonding or lone pair. Those two terms are often used interchangeably. The last thing that's on here, the last rule, is minimize formal charge. The best Lewis structure has the least amount of formal charges possible. And sometimes that's not always 0 formal charges. Are there any formal charges in this structure? Are there any formal charges that I can try to minimize? Take a look at the other side where you looked at common bonding patterns and the charges that they give. Hydrogen has 1 bond. Is that neutral, positive, or negative? Chlorine has 1 bond. Is that neutral, positive, or negative? Neutral. Carbon has 4 bonds. Is that neutral, positive, or negative? Okay, no formal charges in this structure. You can prove it, correct? You can use that calculation and look at the number of valence electrons minus the dots plus lines. But you don't even need to. Once you recognize those common bonding patterns, you know what charge it's going to have. And get to know it now so that when you come to my OChem class, it's an even easier time looking at molecules and understanding their charges. All right, so the rest of, I think the rest of our time today is going to be on drawing these Lewis structures. If you recognize any of them, skip it. Go to one that's a little bit harder for you. I do want to make it clear, this bottom family, that's some ions that you need to know. You can draw covalent structures of polyatomic ions. You need to be aware of that number 1 rule, count the valence electrons. Just to be clear, that is BRO minus, BRO2 minus, BRO3 minus, BRO4 minus. I think the negative charge looks a little small. So I don't want you looking at that thinking there's like a speck on your sheet. Highlight that negative charge so that you know to put that in there. Spend some time on this, and I want to go through one more before you guys leave today. But spend the next 8 minutes or so. Pick at least one compound. Pick the compound you think would be the hardest, and draw out its Lewis structure. Yep. Yes. Now, actually, and these are all valid, but there is a negative charge in each of them, and the way that you've drawn them is that you place the negative charge on the brane. And based on what I've given you, totally valid. But since you're already done with all of them, the negative charge is actually held better by the more electronegative atom is oxygen. So how could we restructure this so that oxygen holds the negative charge in each of these forms? What do you think? Start with the easiest. I think this would be the easiest to figure out. Actually, what does it look like when oxygen holds a negative charge? Mm-hmm. 1 bond, 3 lone pairs. How many lone pairs do you see in a bond? So take these electrons and move them out, and you've got it. Nice. Feel free to work with each other. You're welcome to be collaborative. So you see how it has only not first, but by the end of it, it does. Not for formal charge for octet. So its formal charge is actually plus 2. But we want that in octet. Notice how right now it only has 4 electrons. Yeah, I think I skipped one of my rules actually. This makes sense because normally I have more than this. One rule that you should do is move lone pairs into double bonds and triple bonds for the sake of octets. And I'll give you an example. If you're working on carbon dioxide, this is where you would get up to step number 4. And to minimize formal charge, we need to move some of those lone pairs. What is the formal charge on this oxygen as drawn? Based on that table that you made, -1 and -1, and the carbon's charge would be +2. So how can I minimize formal charge and maximize octets by moving lone pairs to create multiple bonds? Well, oxygen could share one of its lone pairs. So I'm actually going to erase that pair and redraw it somewhere else. Has oxygen lost those electrons? No. Oxygen still has them. Who also has them now? Carbon. We've shared the electrons. Do I have an octet yet at carbon? No. So I can do the same thing on the other oxygen. Remove a lone pair, replace it in a shared position. Oxygen keeps them, carbon increases. Now I have 0 formal charges and satisfied octets.
Remember that sulfur is one of our odd friends, and I noticed that you put the 2 double bonds, 2 single bonds, similar to the one we see on the top. But then you have your fluorine here. It's funky stuff. Halogens like to make 1 bond. So this chlorine having 3 is a really peculiar structure. So what if we take sulfur and put it on the bottom? Notice how it has 6 individual lines? We can just draw 1 bond to each fluorine. There you go. What gave it away? Did you notice somebody else's, or did you think about formal charge? Yeah. How's that going? Good. You know what? This is a good attempt, but actually we're going to find that this oxygen is bonded to one of, sorry, this hydrogen is bonded to one of the oxygens.
You guys may need some context for this molecule. Which is that you should get this framework. This is acetic acid, it's vinegar. And there are multiple ways that you could align it. So I'm going to give this one to you, that you should have this arrangement of atoms in there. Otherwise, it does become really challenging. You could get a structure that exists that just isn't the structure I'm going for.
You got a good idea, but carbon has 2, 4, 6, 8, 10, 12 electrons. So follow that format, or maybe you pick a spot, somewhere else that you can redraw it.
It's okay, I don't know if you're doing it wrong, you're taking a stab at it. And it's a good guess.
Which one? Oh, acetic acid. Vinegar.
Alina will be right there. Yeah, good. Now, which of those bonding patterns do you think is going to be the best for sulfur?
That's not what I meant. I just meant this one earlier.
don't take
No.
one because it's in group 3 or lower.
Actually, best way, don't leave any pairs, unpaired electrons. The best way for that structure is actually a single bond. I don't think you have the right number of valence electrons. 2, 4, 6, 8. But there should be 7 and 6 plus 1. So there should be 16. You only have 8 there. Wait, 7, 6 plus 1. 14. Yeah. Okay. Yeah, because step 4 says use all the remaining electrons as lone pairs. There's 2 ways to do it. I think the way that you were doing it is, I'm imagining oxygen coming in like this. Okay, we don't need to. We just know that that's the way that the oxygen should come. So if you want to do it that way, I can show you how to sketch that. Oxygen. And I'm going to put one dot here, one dot here. Here's carbon, and then we have and also like these are going to be this is all the negative to yeah. You agree? And that's kind of where you got to.
That's not the right. That's a bomb.
What I did there at 6, because I found my rules, not this. You notice how mine doesn't say place the little symbols in there?
Oh, no,
That's what we just did. We placed Lewis in there. So what I say instead is single bond of whose electrons are those? I don't know. I really don't care. No, I heard you have carbon and carbon.
What makes it?
Step number 2. Step 4 is place the remaining electron pairs on the outside atoms. Then on the inside.
Because we only have 13.
How many electrons do I have? 16.
Yeah.
How many have I used? 4. I have how many remaining?
So H's you don't
I'm
need.
going to place them as lone pairs on the outside atoms.
So
You
what?
could be a
Second carbon is going to have a long.
but all the F's just have I don't have any of the options. 2, 4, 6, 8.
Oxygens are going to have 6.
Okay, these are 2 different pillars. Which one is correct? Right, because this oxygen doesn't have
Yeah.
but carbon.
Okay.
This oxygen does.
Let's do a quick math. Okay,
So neither of these ones would be.
Hydrogen, there's 4, right? And then you multiply that by 1.
Yeah, yeah.
That's 4.
They're both
Oxygen,
accurate ways to get
2,
there,
you multiply that by
but
6.
neither of them are finished. So whichever way you want to get to the final
Right?
product
Okay.
is that,
And then I just have to go in and put the dots.
but you're not finished.
Right. Yeah.
Because step
And
5
does it
is
not so they go?
minimize formal charge, maximize bond.
The outer position is.
Well, this is actually wrong because you've got some
I just like
combination
it.
of both there.
Why?
If you've got these lone pairs on carbon, sorry, if you have unbonded pairs on carbon, you should also have unbonded
It
pairs.
doesn't matter. Okay, it doesn't feel like
If you have full pairs on carbon,
but
you should have no
I put
energy
it
for
somewhere.
substances. Yes.
It's because they didn't say like C2.
Octet, right? So then take pairs and share them with carbon.
Two oxygen.
See the stars? Group lone pairs.
So
To make
it's kind of split.
these are no longer going to be non-bonding. Now they're bonding. Oxygen
Yeah, but you put a double bond to the.
to a line, right?
What's
Or if we were doing it this way, this
Yeah.
electron,
So I would
this
have had
electron. All right, guys, we are out of time.
That makes much more sense. Thank you.
I didn't actually get a chance to go through any of these with you, but there is something I want to point out about the bottom row. There are multiple correct answers to this because bromine can expand its octet. This is the best structure for hypobromite, You could show this structure for hypobromite. The only difference is where the negative charge shows up. Which atom holds the negative charge? Well, which atom pulls on electrons harder? Bromine or oxygen? Oxygen does, because it's much further up the periodic table and relatively about as far across the periodic table. So oxygen actually pulls on electrons better, which means this would be the most appropriate structure. This is something I would have accepted because it wasn't what I was testing you on. Both of these are valid. In fact, we're going to start next class by talking about how these are actually related to each other as resonance forms. If you guys don't have any questions, and if you don't want to stick around for student hours upstairs, you are free to go. Have a great day. I'll see you on Wednesday.
Okay. Wait, why didn't you put it on the stand? Okay. So much. It's like, oh, you could do this. Like, one of them is right. Like that thing you would like.
And then look for
Yeah, yeah. Like that's actually so smart. It takes so much thinking.
these would all be
I
negative
also
1,
think
negative
it's
1,
like there's the shape of it. This one. Oh, really?
negative 1, negative 1.
Yeah. It's nice when you know those things. I think I took a biology class like 2 years ago. Oh yeah. It's been a minute. Yeah. Oh,
There you go. You bet. You're welcome, Keon. Have a good day.